So today I'll be walking you through ConfOpt, which is a new hyperparameter tuning package that I recently released an update for. What I'll be doing is giving you first an overview of Bayesian optimization, and then talk about a few of the specifics of ConfOpt and why it differs from most popular alternatives. I'll be touching on source material from these three main papers, as these form the basis for the methodology of ConfOpt, but I won't be spending too much time on what each does or the differences between each. I'll just aggregate all the main findings together and discuss them, or the basics of how they work. Now, what I want to start with is just getting on the same footing when it comes to hyperparameter tuning, right? ConfOpt is a hyperparameter tuning package, and we roughly all know what hyperparameter tuning is, but it's useful to lay the groundwork here. Hyperparameters obviously tend to govern how a machine learning model works. It defines its architecture, and so we say that here, for instance, some tree-based hyperparameters might configure a random forest model instance, and then you can train that configured model instance on an actual data set, and that will return predictions that you can then evaluate on some validation set and get some performance. Now, very importantly, you can't easily go from the performance back to the hyperparameters. So if I wanted to tweak the hyperparameters to pick some better ones, there's no easy gradient step or a back propagation that I can do to go directly from that final holdout performance all the way back up to the hyperparameter values and tweak them easily. So we say that the hyperparameters are related to the performance through some unknown black box function. There's definitely some relationship between hyperparameters and performance naturally, but it's not easy to write down or to extract from the training process, since the hyperparameters alter the architecture of the training process. And so we say that there's this separate black box function process that relates hyperparameters and performance. And this takes us into the concept of the field of black box optimization. And this is a wider field that affects a lot of different areas, but is very heavily applied in hyperparameter optimization. Now, just to redefine quickly what we said before, in a more streamlined fashion, we essentially have some hyperparameter configuration, and then this gets entered into some unknown black box function, and then it returns the performance of training a model on that hyperparameter configuration. The first step here in black box optimization is just peeking into the black box. And what I mean by that is I'm going to sample a random configuration, configuration 1, let's call it. And this has just some random values of the hyperparameters, like 50 estimators and a Gini splitting criterion for random forest. I'll then train a full random forest model on this configuration and record its validation performance. Let's say its validation accuracy, and we get 65%. Then I want to repeat this a couple times, so I might get another couple random configurations and see what their performance is. And now I have some initial indication of how configurations affect performance. So basically I'm just sampling along this true black box function, and I'm getting some examples of how configurations affect performance. The next step is to actually estimate the black box function instead of just peeking these little points along it. And so what we can do is we can just take some estimator like a linear regression and then fit it on the configuration data as our X data and try to predict its corresponding performance as the Y data. And this will give me some equation like Y equals 0.7x, and that's the estimate of the black box function. That's quite literally a function, right? So we now have an estimate for the function of X as it relates to Y. Now, one thing I want to touch on is how to do this in practice. Obviously, we basically want to train on a hyperparameter configuration and predict its associated Y value. The hyperparameter configuration is not readily trainable. It needs to be tabularized, right? Because it's just a dictionary, essentially, of hyperparameter values. And so here I'm just going to very quickly explain how to tabularize it. But the idea is each configuration becomes a row in your eventual training data. and then each hyperparameter becomes a column. So for instance, here we only had number of estimators and criterion. So number of estimators will be a column, and then we have the criterion is a categorical variable, but it only has two values, Gini and entropy. So we can just add a is Gini one hot encoded column, where 1 equals Gini and 0 equals entropy, and that's going to capture the criterion. And that's it. So obviously, if you had more hyperparameters or more categories, you'd one hot encode the categories and you'd add extra columns for the other parameters. But this is the process. And so this is how you can go from raw configurations to actual data that you can train a model on. And so you'd end up with some final data like this, where, for instance, for a configuration that has 50 estimators and a Gini splitter, we get 65% performance, et cetera, et cetera. And the idea is then I train a linear regression on this so that I can glean some patterns about how the number of estimators or the Gini choice affect performance. And then I'll get some equation like this that tells me exactly that. Now, once I have the equation, which again is my estimate of the black box function, I can set some constraints for the hyperparameters that I want to search, because obviously the hyperparameter space is technically infinite. Number of estimators can go to infinity. And then I'll stick those plus my black box function into a linear programming solver, which will give me a polynomial time solution for the maximal value of this equation, right, given the constraints, which in this case is 300 estimators and a entropy splitter instead of Gini. And that's pretty obvious from the equation, because obviously I have a positive coefficient on the number of estimators and a negative one on the is Gini variable, so you have to maximize number of estimators and minimize is Gini. Now, once I have my optimal hyperparameters, the ones that, what I think are the optimal hyperparameters at this moment, given my estimate of the black box function, I then want to train an actual machine learning model, my random forest model, on these optimal hyperparameters, see how well they worked in practice, record the true performance, and then add that data back into my training data. So this now becomes a new row of my training data, and then I repeat the whole process again. I retrain on all the data plus the new configuration I just sampled, and then I again optimize through the linear solver, pick an optimal configuration, and repeat the whole process. So it's this self-refinement process that keeps giving me better and better hyperparameters, and instead of random sampling, I sample based on expectation maximization. Now, some slight caveats on what I just said. The first is, I used linear regression throughout because it's easy to understand and because it gives me a nice actual equation at the end of it. It's really nice for the black box function to actually be a function I can write down. In practice, obviously, there are very complex relationships between hyperparameters and performance, and so linear regression does a very poor job at modeling those, and so we tend to go for more complex and obscure models like random forest or Gaussian process, where I can't write down an equation for the solution, but it'll model the actual relationship between x and y better. And here, the optimization also slightly changes. Again, I can't use a linear solver. I have to instead take an iterative approach. So basically what I'll do is I'll sample all the hyperparameter configurations within my constraints. So like just exhaustively try all combinations of hyperparameters that satisfy the constraints. And then I'll pass them through my trained random forest model or whatever model I chose. I'll get an expected performance for y, like this is what the model thinks will be the performance for this hyperparameter configuration. And then out of all the hyperparameter configurations that I could sample, I'll sample the one that has the highest expected performance. This is the same basically thing as the linear solver, except it's going to do it in a sort of a brute force fashion. Now, this takes us to the topic of exploration, because basically what I've described up until now is exploitation, meaning we're being very greedy, and at each time step we're picking the hyperparameter configuration that maximizes our expectation of what's going to happen. So we're constantly maximizing the expectation. And this can be good sometimes if the search space is very simple. But a lot of the time, it will actually result in even worse than random performance in the long term. And let me explain why. So here I have a simple example where I have only one hyperparameter x, and then some corresponding performance y. And then this green line models the true objective function that maps the true relationship between x and y. I then peak some points, let's say 8 points along the true objective function. And then I fit an estimator, right? Now, before we did linear regression, this time this is a Gaussian process. So I fit the Gaussian process through my 8 data points, and I get a line of best fit that looks like this. And this blue line essentially is equivalent to that process I described of plugging in each value of x, or of your hyperparameters, and then seeing what predicted performance you get. And then the idea is, as we said before, we want to maximize the expected performance. So we want to sample at the x that results in the highest predicted y. And that's going to be somewhere around here, right, between these two sample points. And so we sample there, and we go from a best value of 3.93 for our y to a best value of 4, which is awesome. Now, what happens next? What happens next is I have nowhere else to go. Because if I want to sample another hyperparameter configuration, all I'll end up doing is sampling a point that is a little bit to the right of the previous one. Because there's literally nowhere else on the blue curve that maximizes my expectation, right? And so what ends up happening is I get stuck in this local maxima for a really long time until I exhaustively try all values of x in this range, and then eventually I'll move to the right. And so in essence, I will completely miss out, or it'll take forever before I get to it, this second global maxima that actually has the true solution to the problem. So we need to add a little bit of exploration into the mix. And I'm just going to reset the graph here. So we have our 8 points, same objective function. I'm going to fit my GP estimator. But this time I'm going to introduce a little useful fact about Gaussian processes, which is that in addition to giving you a line of best fit, like most regressors, they can also give you a 95% confidence interval, or any percent confidence interval. And so it gives you these uncertainty bands at every x point that tell you not just the mean, not just the expectation, meaning the blue line, but also how uncertain the model is about that expectation. And what we can do is now, instead of sampling at the expected value, meaning maximizing the blue line, we can instead sample on maximizing the 95% confidence interval. So basically the logic here is, instead of going with the thing I know with high probability, or with high confidence gives me a good value, I'll instead take a chance, and I'll be like, well, I'll sample at the thing that with very extreme probability might give me something that's better than the expected value. So basically, we're just taking an optimistic approach and constantly sampling at the extreme probability end of my expectations, so that we also consider the impact of uncertainty, and we sample in areas where there's a large y spread and there's some maybe small possibility, but still a real possibility of achieving very high y values. And so if we do this, for instance, we'll end up with this first point as our sample. After you sample, you refit the GP, as I mentioned, in that self-refinement process, which then means you also refit or update the confidence intervals, which get narrower at the point that we just sampled and larger otherwise. And then we keep just repeating this process. So I'll just play out a couple of steps here. And what you can see is eventually, in just 5 iterations, we converge to the almost, it's 5.99 instead of 6, but almost to the true global optimum on the right. So we don't get stuck on the left. We instead keep exploring, because there's this big region of space to the right that we hadn't looked at all, where we didn't peak any points. And so the model is like, well, yes, we can maximize expectation on the left, but the confidence intervals on the left were really, really tiny. So instead, actually, you should explore this area to the right and dispel any suspicion that there might be better values there before we exploit. So that's exploration, right? So we looked at exploitation, we looked at exploration. Now let's look at some formal acquisition functions. And what I mean by this is all these things I described, sampling based on expectation maximization, or sampling at the upper confidence interval. These are sort of rough heuristic acquisition functions, meaning a function that defines how you should acquire the next hyperparameter configuration. Now I just want to talk through some of the more formal ones, just to give you an idea of how this usually works in practice. So the first one is probability of improvement. Probability of improvement is actually a very bad acquisition function, but it's the easiest complicated one to explain. So basically here we have the same exact data we had before. It's just squished, but it's the same data, same objective function, and same 8 points. And then I have my GP estimate and the confidence interval, right? The 95% confidence interval. Now, I told you that we can generate these shaded intervals in a GP, but I didn't tell you how, and I still won't explain the math, but the rough logic is that the GP can produce a posterior normal distribution for the range of y values at every x point, okay? And so then the way it gets the interval is just by saying, oh, you want a 95% confidence interval? Great, I'll just take the 2.5th percentile and the 97.5th percentile of this normal distribution, and I'll just return those two bounds. So you can pick any, again, percentage interval you want. It'll just subset those two bounds along the normal distribution and give them back to you. But the raw output of the GP is actually a full posterior distribution for y at x. And this is amazing, incredibly powerful. And what we can do with this is develop more formal acquisition functions. And one that's quite easy to glean is probability of improvement. So here I'm going to say, okay, I have my 8 points that I've sampled so far. And let's say we pick a slice for now to focus on, which is x equals 5, right? There's technically posterior distributions for every value of x, but let's just look at x equals 5 for now. And we have this posterior normal distribution. Now, I can take the best hyperparameter configuration point that I've sampled so far, meaning the one with the highest y, and then I can draw a horizontal line that cuts through the posterior distribution at x equals 5. And because of just, basic distribution rules, the area above where this line dissects the normal distribution is going to tell me the probability that if I sample at x equals 5, meaning if I pick x equals 5 as my next hyperparameter configuration to actually train on, this shaded area is the probability that I'll get a value that's better than the one that I currently have, meaning larger than the current best y value. And that's a really amazing thing, a really robust thing, because I'm using the actual posterior distribution to get an exact probability of improvement based on my current best y value. And so we can just write this down. This is about 18% in this case. We can just write it down in a second chart here where I keep track of all these probabilities of improvement. And then the idea is I want to slide to another x value. Let's say x equals 4. And again, I'll get the posterior distribution at x equals 4. In this case, it's a little bit tighter. And so we have a smaller probability of improvement because there's less area under the curve at that intersection point of my best y value. There's less upside potential. And so we jot down that point. And then I'll repeat this again for, let's say, x equals 3.5. And then here the distribution is very tight because we're approaching the points that we actually peaked. And so the uncertainty around those points is much smaller than in the middle of the x equals 6 or x equals 7 range. And here there's basically virtually zero probability of improvement. And the idea is you want to keep doing this over and over again until you have an actual line for the probability of improvement at every single point x of your hyperparameter space. And then we sample the next hyperparameter that maximizes the probability of improvement, which is at this x equals 2.5 range. And then you actually train a model on that hyperparameter configuration, retrain, repeat the probability of improvement, et cetera, and you get into the old loop. So this is a much more robust way of doing things, because it's distributionally grounded. It's based on actual math and probability of improvement given your current best, and then that current best y value obviously keeps changing, right? So if I get lucky and I sample a better y value now, I'll also increase that horizontal line's y value, and so it's this constant self-refinement process. So that's probability of improvement. Another one that we can quickly talk about is GPUCB. This stands for Gaussian process upper confidence bound. And basically here we have a similar concept, but it's a little bit more heuristic, at least at first glance, but there's actually a fair bit of math that makes it robust. But here the logic is, again, same graph, just less squished. So I have my GP line, I have my true objective function in green, and then here I've just picked a random x point, 4.7 or something, and I'm just going to retrace, the fact that we have this normal distribution, this posterior distribution at every value of x. And obviously this is a normal distribution, so it's parameterized by the mean and the variance. And what that means is I have access to the mean and the standard deviation at this point x, right? And so a simple function that we can come up with, a simple acquisition formula, is something that looks like this. And what this is basically saying is we're going to maximize the mean plus some trade-off parameter, which this whole big term will just simplify to a constant. So don't worry about it. Treat it as just b. So basically mean plus trade-off parameter b times the standard deviation. And what this is essentially saying is just saying, okay, I'm going to look at the expectation, which is the mean, plus some, sensitivity parameter b times the uncertainty, which is the standard deviation, right? So it's basically just expectation plus trade-off times uncertainty. And the trade-off parameter here is just something that quantifies how much I want to explore versus exploit, right? So for b tending to infinity, I'm basically doing random search, like pure exploration. And then for b tending to 0, I'm doing pure greedy search because the standard deviation term just cancels out, it becomes 0. So that's GPU-CB. And then this b term is this complicated b term that you see here. Again, it is a constant, but it's derived mathematically so that it matches certain finite convergence proofs. So that's GPU-CB. And then there are heuristic versions of this. So the GPU-CB is theoretically robust, and this b value is derived again to match convergence proofs, but then there are many heuristic versions of this kind of exploitation plus trade-off times exploration thing, right? The standard deviation here could have just been the width of the confidence interval, or it could have been, any other measure of uncertainty. And the b parameter doesn't have to be this. Again, theoretically it has to be this, but then for a heuristic approach, you can make it converge faster, you can make it converge less fast, you can prioritize exploration or exploitation, etc. And then there's a bunch of other acquisition functions that I'm not going to get into, but basically, yeah, there's quite a big choice, and they all have strengths and weaknesses in benchmarks. Now, what's the problem? The problem in everything I've described so far, you might have noticed, is an over-reliance on Gaussian processes. Pretty much everything I walk through is a Gaussian process method. And the reason for this is traditional point estimators have no way of generating conditional distributions at x, meaning these little posteriors at every x along my curve. Most point estimators just give you the blue line, right? The blue line of best fit, where they tell you the conditional mean at x. They can't tell you the full conditional spread of y at x. That's a very powerful thing that only Gaussian processes sort of can do. And this is, it's good and bad. Gaussian processes are very good models that work extremely well in low data, extremely well in continuous data, et cetera, but they do have some very real weaknesses. And one of them, for instance, is they don't work well in categorical data. So if you have a lot of hyperparameters that are categorical, and you have a lot of values for each of those categorical hyperparameters, then the GP might struggle a bit. The other GP weakness is these posterior distributions don't come for free, right? You have to assume a normal distribution in order to parameterize a posterior normal distribution. So basically, we're just saying, well, the data is probably normal at x equals 5. The y spread is probably normal. Here's the normal distribution that best fits that data if it's normal. But if the data isn't normal, if we have a lot of skew, if we have long tails, then this normal distribution doesn't fit very well. And all of a sudden, all these fancy probability of improvements and guarantees and convergences technically don't really work anymore. They just work on paper. So these are the two biggest weaknesses of GPs. And so to fix this, we can look at something called Quantile regression. And this is the foundation of the three papers, the source papers that I mentioned, and the foundation of ConfOpt. Quantile regression, just as an overview, let me start actually. So let's say we have some sample X and Y data. Generally, we would fit a point estimator right through this. And let's say we're fitting a gradient boosted machine model. This is what the line of best fit would look like. It cuts through the data, it estimates the conditional mean, and it does this by training on a mean squared error loss, right, between the observed Y and the predicted Y, which we're all familiar with. Now, Quantile regression is similar, and it works on any model, so we can still fit a gradient boosted machine model here, but we change the loss that it uses during training. So instead of mean squared error, we use something called the pinball loss, and that's equivalent to this formula here. And this is just a simple, I'm not going to spend too much time on it, but it's a simple over coverage and under coverage penalty loss. And so basically, if the true Y value is above or equal to the predicted value, then use the first row as the loss, otherwise use the second row as the loss. And without really getting into the weeds here, what you can see is that this is a really simple loss, meaning we still only need the same unknowns as the mean squared error. We still only depend on the true Y versus the predicted Y. And then the only extra term is this T value. And T stands for the quantile that you want to predict. So for instance, for T equals 0.9, my dark blue line of best fit here is not going to show me the conditional mean at X, which is what most regressors do by default. It's instead going to show me the conditional 90th percentile value at X, right? So and you can see it's a fair bit higher than the orange line, because again, it's not predicting the mean, it's predicting this higher end of the conditional distribution at X. And you can change T as you want. So for instance, T equals 0.5 would give you the conditional median at X, and so on and so forth. Now, why, how do you use this for hyperparameter tuning? Well, this is actually roughly equivalent, or, it can do a lot of the things that Gaussian processes can. And as an example, I'll just focus on probability of improvement as my acquisition function. So let's get rid of the mean. That was just for explanation purposes. I'll keep the 90th percentile quantile line here. And then what I'll do is I'll train a bunch of other quantile regressions, each with a different target quantile. So I'll train a 10th percentile quantile regression. I'll train a 20th percentile quantile regression, et cetera, until I get to 90. And I'll do this in equal spacings of 10. So, we go 10, 20, 30, 40, et cetera, until we get to 90. And what you now get is, if I pick a random X point, like X equals 5, if I trace a line upward and take the cross section of the Y values of the quantiles, I now have this discrete approximation for the conditional distribution of Y at X, right? I have these 9 quantiles, these 9 values for how Y is distributed along X conditionally. And for enough quantile regressions, if I trained an infinite amount, right, or 1,000 or something, then theoretically, if they were all well calibrated and predicting the right value, this approximation would tend to the true distribution, right, the full continuous distribution. And this is basically the crux of it, is that I can use these quantile regressions to approximate what the GP does naturally, which is just output this nice, smooth, continuous posterior distribution. But I can do it with, and obviously once you've done this and once you have this approximation, you can use it to calculate probability of improvement, just like we've seen, because all we need is a posterior distribution for Y. You can use it to calculate all sorts of other acquisition functions, so it can roughly replicate almost everything that the GP could do in terms of flexibility and in terms of giving you this conditional distribution at X. Now, it just sounds like we've done a lot of extra steps to just circle back to where we were with the GP, but quantile regression and this approach specifically that you see has a few key strengths that take it that extra step forward. And those are, first of all, better categorical hyperparameter handling. Why? Because we don't need to use a Gaussian process as an estimator anymore. We're unlocked from that dependency. We can use a tree-based estimator that works very well natively with categorical hyperparameters like gradient boosted machines or random forest or any other model that you think would work well with categorical parameters. The second thing is we make no distributional assumptions, right? We don't need to assume a normal distribution. We're only interested in the quantiles, meaning the probability concentration along the distribution, but we don't care what distribution it is. So it could be as messy as multimodal as you want, and we still only need to look at the concentration of y values at each quantile. We don't care about the actual assumed shape. And for enough quantiles, we can perfectly approximate this irregular distribution. Whereas a GP would have to force a poorly shaped normal distribution onto this clearly non-normal data. And then this is basically a subset of the previous strength, but because it doesn't assume a normal distribution, it can also handle skewed data. So for instance, here you can see some data where the data is roughly uniform from 3 to 4, and then from 4 to 6, from x equals 4 to x equals 6, it sort of explodes a little, and you get this very long upward tail distribution of y, and so the data is heavily skewed, and also you get this hard floor at y equals 100 or so. And so here, all I have to do is I can fit a 25th percentile and 75th percentile quantile regression through the entire data, and that will perfectly approximate it. And again, here I'm just fitting 2 regressions, but I could fit many, many, many more, and then I would have an actual estimate of the conditional distribution at each x of this curve. Whereas if I was using a GP, I'd have to, again, at a given point x, here I'm just going to pick one, x equals 4.7, I would have to force a normal distribution to the data, and I would end up underestimating all that upward sprawl in y, and I would end up overestimating all this probability mass that doesn't even exist at the bottom here, because again, the y value caps off at y equals 100, but the normal distribution can't really parameterize that. It doesn't have a way to understand that, because it needs, for observations to be symmetrical, it needs to assume that the same spread of y values is above the mean as is below the mean. So broadly speaking, we have a much more flexible and more robust hyperparameter framework that can handle a lot more that is thrown at it, while still matching all the nice distributional properties of the Gaussian process. And then here I'm just going to talk, I'm not going to talk a lot about this. I'm just going to give a little synopsis about conformal prediction, because it's a big part of the methodology and of the papers, but we don't have time to cover it today. But basically, the pinball loss that we looked at, that gives us the quantile regression, is good. It's a very good loss, and it will hold, but it needs certain assumptions as well. They're not distributional assumptions, but they are assumptions. And so it assumes infinite data, as in it will, the guarantees of pinball loss hold for infinite data, and zero model misspecification. That means, you're not trying to fit a linear regression to nonlinear data, for instance, which would just give you consistently biased estimates regardless of the loss. So these are the 2 key assumptions. And, a lot of the time these are met. I mean, model misspecification is reasonably easy to handle if you use a sufficiently complex learner. Infinite data is obviously impossible, but this is a limit. So as you approach a large amount of data, the idea is that pinball loss gets more and more accurate, and so you will end up closer and closer to your target quantile. At the same time, though, the problem is in hyperparameter tuning, we rarely deal with large amounts of data. We're often dealing with, 50 hyperparameter configurations throughout the entirety of search, maybe 100 if people have a large budget and a lot of time to spend, but generally you'd never try thousands of hyperparameter configurations, because it's very expensive to train a model on all those hyperparameter configurations. So we need a way to make these quantile regressions actually work on small amounts of data, and the best way to do that is through conformal prediction, which is a calibration wrapper around the regression. And so basically quantile regression plus conformal prediction results in valid quantile predictions, even on small data sets, even on limited data, and also technically under mild model misspecification. Good. So then that takes us to results. So here I just have a small results snippet comparing how all this new methodology, the quantile regression methodology in ConfOpt, compares to existing alternatives. And here I have two benchmarks. One is JAS 201, which is a convolutional neural network benchmark tuning across 3 image recognition data sets. And then here I have LC-Bench, which is a feed-forward neural network tuning benchmark that looks at, in this case, 5 large classification data sets. The full LC-Bench has 32. This is a subset version. And what you can see here is that generally ConfOpt outperforms all alternatives consistently across both benchmarks, and these are very representative benchmarks of real-life use cases, and can go very heavy and sort of complex in terms of resources. And the interesting thing, though, also is, yes, it outperforms consistently, but it massively outperforms on JAS, and it only slightly outperforms GPs on LC-Bench. Actually, sorry, let me rephrase. So it always consistently beats up Tuna, which I'm benchmarking here with the default TPE sampler, but it situationally outperforms Gaussian processes or GPs. So on JAS, we get a lot of outperformance, and not so much on LC-Bench. And that's because JAS is a mostly categorical hyperparameter benchmark. There's, I think, just 2 numerical hyperparameters, whereas LC-Bench is an entirely numerical hyperparameter benchmark. So if you recall, GPs aren't so great at categorical hyperparameters, but they are quite good actually at numerical hyperparameters. And so that's why GPs perform quite well on LC-Bench, and they're almost the same as ConfOpt, but they struggle a lot on JAS. Great. So then I'll just leave you to some resources, which I'll link in the description. But here we have the GitHub repository, the doc site, the PyPy package, and then the actual paper that has all the detail that I mentioned, in addition to the 3 papers that I mentioned at the beginning. And if you do go to the GitHub repository, definitely consider giving it a star. It helps. Cool. Hope this was interesting.